Hello, welcome to another Stat 432 video. I already screwed up the intro and clicked the wrong scene, but I'm just going to go with it because I need to do a video. The show must go on. I know this isn't going to be my best video, but I need to do one, so here we are. You didn't need to know that, but I'm saying it. Okay, so everything we've done so far in this class, I would sort of file away under basics, fundamentals, maybe even old school, like the most tried and true method. So we've looked at, ordinary linear regression and logistic regression in the classification setting, maybe the most go-to models that there could possibly be. We looked at k-nearest neighbors in both regression and classification, which is a useful model for introducing the idea of non-parametrics to you, but maybe not the most useful thing in practice for various reasons, but something necessary to study. And then we looked at trees in both cases. So all of those are sort of very fundamental, very basic methods. What we're going to do this week and next week is look at sort of what I would call modern extensions of some of those methods. So in this video, we're going to talk about sort of a twist on linear models that's a little more recent. And then next week, we're going to sort of look at how to put a more, what's what we're looking for here? Put a more interesting twist on trees. Spoiler, we're going to use multiple trees and we're going to call it a forest, but we'll save that for later. Okay, so we're going to introduce the idea of regularization in this video. But the first thing we're going to briefly talk about is a concept that you've hopefully seen before. I'm just going to sort of refresh your memory on real quick, which is something called best subset selection. So this is the idea where, okay, so we want to fit a linear model and we have p feature variables. Well, there are then 2 to the p possible different models we could make using the available variables, right? So we could start with using none of the feature variables. That would be an intercept-only model. And so I would call that a zero feature model. So we're looking at this row here, and there are exactly one of those. We could look at all of the different models that use one feature. So just using x1, just using x2, and so on and so forth. There are p different ways we can do that for each of the p variables. We could consider models that have 2 of the feature variables. So x1 and x2, x1 and x3, x1 and x4, and so on and so forth. And it turns out there are p choose 2 of those. And we could keep doing this. We could consider models with p minus 1 variables. And frankly, that's just too much to write. I'm not going to do it. And then lastly, if we use p feature variables, well, there's only one way to do that when you have p available, and that's the full model. And one of the things you could do is you could say, well, I want to know which of these is best. So what you would do is you would fit all of them and use whatever metric you felt appropriate, maybe something like AIC, and then you pick the best one. The problem with that is that if you have a lot of features, that's going to be a lot of models you got to fit. You got to fit because of the way the combinatorics work here, there's 2 to the p possibilities. So generally, we don't really want to do that. So what do we do instead? So one of the things that, again, hopefully you've seen before is this idea of a stepwise search procedure. So if you take a direction to step, so you can either go backwards, forwards, or do a little bit of both searching, and then you add together that with a metric, say AIC, BIC, mallow CP, or some other thing that you're interested in, you can use this together to create a procedure to sort of search through the model. So say we're going backwards in AIC, right? So let's start with the full model, and then we'll consider deleting each possible variable, right? And then we say calculate AIC on all of those and pick the best one. Then within that model that we picked at that step, we again try to delete a variable, pick the best AIC, and go on and so forth. So that way we're searching through the space in a reasonably well thought out way. So we'll probably get a good model but maybe not the exact one we would have gotten from a best subset selection. So a couple notes here. Backwards plus AIC is a very common thing to do because that is a default in R. So if you use the step function in R and give it a linear model and don't tell it anything else, it by default is going to perform a backward search using AIC as its sort of metric of choice. And one thing I might note here is that the AIC is related to the leave one out cross-validated error asymptotically. So if you did say leave one out cross validation to select a model versus doing a backward selection with AIC in certain large sample settings, those will sort of converge to each other. But that's just sort of a minor point. But right, so this is the idea of variable selection, and we're interested in variable selection in so much as it could potentially get us a better model to make predictions with. So this is something totally, if you have a big feature space in your model, so you have a lot of feature variables, you might want to reduce that down. And you could very well try something like this. So you could cross-validate even the entire procedure of fit a model, do backwards AIC, get the cross-validated error on that to see how well it's working compared to, say, other things. But what we're going to talk about is a completely different way of tackling this problem. So we have to start with sort of a ridiculous example. So here I have some data that was generated from some true model that I wrote down here. I frankly don't even know why I wrote down the true model because it's not entirely relevant. Okay, so, we want to do the usual least squares thing, and that's what I have written down here 3 times, which might seem sort of silly, but bear with me. Okay, so if we did least squares, and I'm just going to focus on the beta 1 parameter, suppose with this data, I don't know, it looks something like that, I think, and we would end up with beta 1 hat equal to, I don't know, 5.2. I'm making these numbers up, but I think that wouldn't be super unexpected if I told you that the thing we had up there, that was the true model. So we generate some data, there's some noise in the data, our estimation is not perfect, we get 5.2. Okay, great, that's fine. What if I constrained the minimization that you're doing here? So instead of just saying, well, consider all possible values of beta 0 and beta 1 and find the ones that minimize the least squares, what if I added a restriction? So I said, do this subject to a constraint. And that constraint is going to be that beta 1 has to be less than or equal to 3 in magnitude. Again, silly in this case, but we can think about it. So I think if we did that, and this drawing is not to scale, it's for illustrative purposes only, I think we would end up with a fit something like this, and I'm going to go ahead and say that's beta 1 hat would exactly be 3. Because we need as much slope as we can get there to minimize the errors as much as possible, but we're bounded by this constraint. We can't let it go past 3, so we can't be, 3.1, 3.2, which would all be better. This is as good as we're going to get. Okay, great. Or we could take this to an extreme. You always got to go to the extreme. So what if we did the same thing, but we made our constraint as ridiculous as possible and said, okay, beta 1 must be less than or equal to 0 in magnitude? Well, I'm pretty sure there's only one option for the result of that minimization, and that would be that beta 1 hat is 0. So I think, again, eyeballing it, that would be something like this. Okay, so in this case, it's probably, the 2 constrained models are clearly not good here, but I want to indicate something that's happening here. If we think about the bias variance trade-off a little bit here, so if we think about the variance is clearly lowest with the most constrained model, because effectively this is an intercept-only model, but we're just writing it in a very goofy way. And as we go this direction, the variance increases. I think that sort of goes without saying. I think you'd realize that if we generated new data with the most constrained model, we would get 0 again. With the medium constrained model, we'd probably get 3 again. And with the unconstrained model, we'd probably get something that's close to 5, but it's going to be a slightly different value every time. Meanwhile, if we think about bias, it starts as an unbiased estimator and gets more and more biased. Like in the last model where we're constraining it to 0, that's a heavily biased model. But remember, there's this bias variance trade-off. And sometimes, what we'll find here, is not in this case, but in what we're about to talk about, if you add a little bit of bias, sometimes that decreases the variance enough to get a better mean squared error. So that's the idea we want to play with today, is we're going to constrain our model search in the hope, or in our estimation, in the hopes that adding a little bit of bias reduces the variance so much that we get an improvement. That might not be absolutely clear in what we're about to show, but that's the general idea that we're going for. Okay, so I want to talk about some geometry for a second. So this is going to be kind of the standard visualization that illustrates what the two methods we're about to talk about. Okay, so I'm considering a linear regression problem where I have two feature variables, x1 and x2. And this is not a picture. Let's be very clear. These two pictures are not pictures of the data, and I'll explain them in a second. But let's suppose that I did least squares, and I'm going to ignore the intercept. We're going to be doing a lot of ignoring the intercept here. But I fit least squares to some data, and I get beta 1 hat is 4, and I get beta 2 hat is 2. And that would be the least squares estimates. Okay. But now I want to imagine what would happen if I redid the same problem, but with some different constraints on not just one variable, but beta 1 and beta 2. So on the left-hand side here, I have a picture that represents what would happen if we tried to do this estimation subject to the constraint that beta 1 squared plus beta 2 squared is at most 4. So what that means is that we're only going to, and so these axes, so the x-axis here is beta 1 possible values, the y-axis is x2 possible values. So what we're saying is we will only accept beta 1 comma beta 2 combinations that are within this shaded region here. So what these ellipses are next door, or not next door, but right next to it. So I've marked the point beta 1 is 4, beta 2 is 2, and that's the blue dot there, and I've indicated that that's the least squares estimates. So what happens is these contours that are circling this, or ellipsing, I don't know how to say that correctly, but the contours surrounding it, basically what they are is if we move away from least squares, let's say this sum of squares is going to get worse. It just turns out that in an ellipse around the true least squares value, you get the same sum of squares there. That's not super important. But so basically, the minimum sum of squares happens at the point for the least squares. So that first ellipse is sort of, they all have a bigger mean squared error, but it's all the same. The next ellipse has an even bigger mean squared error, but they're all the same, and so on and so forth. So what happens then is we want to look for where one of those ellipses meets the circle, which in this case is right about here. So in this case, we would get beta 1 hat is 2, and beta 2 hat is 1. Okay, so this is what we would call shrinkage. So by adding a constraint we have shrunk the value of our estimators in magnitude. You could also take a -1, it would get closer to 0. Um, and the way that worked is we found the beta 1, beta 2 that gives us the smallest sum of squares error here within the constrained region. So that's why we found where the ellipse meets the shaded region. Okay, cool. What if on the right-hand side we looked at a different constraint and you sort of accepted my artistic failings? I'll get to that in a second. So here, instead of looking at squaring the individual coefficients, we're going to look at the absolute values of them. So when I do this, so I'm doing this minimization. I should really write. We're trying to minimize this, right? I mean, that's what you do, right? Anyway, so here I have a different constraint, and it looks like this diamond-shaped thing. So I want the sum of the absolute values of the coefficients to be at most 2. So anything in this region, again, it's not to scale. Pardon my artistic abilities or lack thereof. Okay, and then so it's supposed to be the same exact ellipses in both cases, and I tried to draw this as close to what I needed as possible. Something interesting happens because of the geometry of this constraint. So on the left-hand side, we had a circle, which is decidedly not pointy. But on the right-hand side, we have a thing with points on it. And when you have points on this square thing, it's more likely that the ellipses are going to hit a corner. The way I've drawn it, it's close, but we're just going to fudge it and say that it happened. So here we get this. So here we would have beta 1 hat is 2, and beta 2 hat is 0. So this is interesting. This is interesting. This is interesting. Not only did we get shrinkage, because we're, 2 is less than 4 and 0 is less than 2, we got a 0 here. That's, I mean, maybe it's not obvious why I'm so excited that that's 0, but that means that what we effectively did by having this constraint was variable selection. We said, well, beta 1 is in our model, and x1 is in our model, and x2 is, well, we fit the model with x2 in it, but now we're setting its coefficient to 0, so we've effectively kicked it out of the model. So this procedure on the right with this pointy constraint, it does variable selection. That's cool. So let's give these things some names. Okay. So here I have 3 sort of big statements, and we're going to go through them one at a time. But the things that they share in common is this thing that we have here, I would call this, it's the sum of squares error in your usual least squares thing. And then here is what we're going to call our constraint. So we're still we're minimizing the sum of squares, but we're putting conditions on where you can search within the betas. Okay, so what is this S thing? So I'm going to call that, for now, I'm going to call it a budget. So essentially, I can give you a big budget, so a big S, so that means you have a lot of value to work with your betas when you're doing this minimization, or I can give you a small budget, and you have to be really careful where you allocate the magnitude of the betas. So when we do this, and when our constraint is the sum of the coefficients squared, and we'll never include the intercept there, this is called ridge regression. It goes by a couple other names, and it's been around for a little while now. That is one form of shrinkage or regularization. We would call this regularized regression. Okay, cool. So if we move to the second line, so now the sum of squares thing, that's the same, but the constraint now, instead of squares, it has absolute values. So ridge is the picture on the left here with the squares. So the new thing that we're looking at is the thing with the absolute values, which creates the points. This is called the lasso. oh no, I'm gonna blank on lasso. It's like least lasso. It's an acronym. It's like least angle. I should know this. I'm embarrassing, but it's also like a lasso, like a cowboy would use, and it's like it's pulling in variables to the model. I think that's the idea. Um, anyway, I'll drop the reference to that in the reading so you can least angle. One of the S's is shrinkage. I should know this. Do I have a? I don't want to change my screen to Google it. Will Bishop have it for me? It's embarrassing. I should know these things before I make a video. Lasso 145. Well, so of course it doesn't tell me. Oh, I guess I should mention this was done by Tib Sharani in 1996. So today's video brings us into what I would call the modern era of sort of like statistical learning. So note that modern here means roughly the 90s. So I think that makes me feel old, but what are you gonna do? Okay, least. Lasso. Of course not. Anyway, it's not important. The L is least. The A is angle. I think one of the S's is shrinkage, but not important. Not important. It is important, like the lasso, like a rope, like a cowboy would use, because it's the idea that it ropes some variables into the model and others not, because it does variable selection. Okay. This last thing here is interesting. With this weird constraint I have, where basically I give you a budget and every variable you include in the model counts as one against the budget. This is actually best subset selection that we saw at the beginning. So basically, if I use the budget, the S, as a tuning parameter, if I go from like 0 to P with it, well, then you'll try all the possibilities. It's just a different way of writing it, but you would do the same thing. Okay. So something I should really mention here is that Ridge and Lasso are great when P, the number of features you have available, is large. So using the sort of lasso idea here doesn't really make sense. Here, it's still probably not obvious to you that it's a good thing to do. Here, well, now we're talking about an arbitrary P, but the bigger you make P, that's where these things really come into their own. And remember, lasso does selection because of the geometry we see here. This idea that it works better with big number of features, and the idea that it even does shrinkage and variable selection is something that you're going to explore when you get into R and start doing the quiz material. But for now, you'll just have to trust me on it. I think that's better learned by doing. Okay, so an important point I need to make here. So far, I've been referring to this notion of there's the sum of squares that we need to minimize subject to some constraint. And we'll focus on lasso for a second. So something you should realize, if the budget S is 0, well, that would be fitting an intercept-only model, right? So if I allow for 0 magnitude in all of the coefficients in front of the features, well, that's just an intercept model then. Whereas if I give you an infinite budget, well, that's just regular old ordinary least squares. Great. I want to rewrite this problem. So now it's going to be a minimization where we're considering simultaneously minimizing the usual error thing plus this thing here that I'm going to call a penalty. And instead of a budget, we now have this lambda, which I'm going to call a tuning parameter. So this penalty, it's basically how do I explain this? It's looking at the magnitude of the coefficients, right? And it turns out that there's a trade-off between the error and the penalty. So, let's see. As the least squared error goes down, so that is the thing on the left, as that goes down when you're considering different betas, that generally means that the penalty goes up. Because basically to fit the data better, you need to use more magnitude on the coefficients. It's kind of what we saw in this ridiculous example here. The bigger I let the beta be, the better it fit the data. But in doing that, the bigger I let the beta be, the bigger then this penalty term is going to be. So lambda then is a tuning parameter that controls that trade-off. So maybe you can see where we're going. We're going to tune for that. But so there is a correspondence between writing this in terms of the sort of like a constraint with a budget and this lambda with a penalty. And there's a correspondence between the two, but we're not going to worry about that. But just know that you can think about this general idea both of these ways. But the way we're going to look at it in R is this penalized approach. So we're going to tune for a lambda value. And so we've called this shrinkage. We've called this regularization. Sometimes we'll call it penalized regression. So this is a really common setup in statistics where you have like an error and a penalty, and you want to sort of like deal with the trade-off between the two. But similar real quick, so just for thinking about this, if lambda is 0, well, that means there's no penalty, and we're back to ordinary least squares. If lambda is infinity, well, that means that as soon as you put any magnitude on any of the coefficients, the penalty term becomes infinity, and that's a bad way to minimize things. So you end up with an intercept-only model. Okay, so before we talk about fitting these things in R, we need to talk about one important detail. So if you understand that we're sort of creating this budget or this penalty, the size of our coefficients really matters, right? And especially the size relative to each other really matters, right? Because if one of the coefficients is sort of just naturally bigger than another, it's going to probably get penalized more. But it turns out in least squares, you can sort of manipulate the coefficients to be whatever magnitude you want. Well, how would you do that? Well, this idea here. So suppose I have some really simple regression data here. And instead of the original x that I'm given, I'm going to create a new x, and I'm going to call it x star. And how I'm going to do that is I'm going to standardize. So I'm going to take the values of x, subtract off x bar, and divide by the standard deviation of x. So I'm making up these numbers here, but so suppose that the mean of this original x column was that million. So now that becomes 0. And let's say that 900,000 becomes -1 and something like this. So like the standard deviation was 100,000. Okay, great. So now I'm going to fit two regressions. I'm going to fit one using the original x and another using the scaled x. Well, so then in the original one, I end up with, let's say, a beta 1 hat of 0.001. So now if I do this in the with the modified, I'm going to get something like beta 1 hat is 1,000. I might be off by a decimal place in one of these, but the idea will be the same. So if you think about using this versus this, that'll have a big effect on, adding these things together. That would be like that. So now imagine that you had two variables in this data set, in a data set that you're fitting a model to. One on the orders of magnitude of millions, and another on orders of magnitudes of like, 1/10 of 1%, right? So like the betas that you're going to get out of these, one is going to be really small, one is going to be really big, but then we're trying to compare them in this sum. So what this means is that before you do these penalized regressions, you should always standardize all your variables. That's a topic that we're going to return to more broadly, where we consider some practical implications of doing machine learning. But I should note here that there's one other model where you don't have to do this, but I think we even mentioned that it's something you want to consider, which is k nearest neighbors, because depending on the scaling, that'll change the distances between points. But again, more on that later. But just note that it has to be done here. Well, I guess you don't have to do it, but it's highly recommended. So much so that I'm going to make a comment here. So how do we do this, right? So I'm talking if you're looking at this and saying like, oh, I don't know how to do this minimization, don't worry, I'm not going to make you do it. Actually, that's not true. If you're a grad student, you might have to do it for the ridge case, but that's for a different day. We're going to use R to accomplish this stuff. And I think I'm going to be a little unhelpful and not do an R tutorial on this. The quiz this week, if you're doing this in the fall of 2020, is not going to be particularly long. And I think if you wrestle with this one function that you really need, you'll get a lot out of it. And I'm really hoping we're getting to the point where you've seen so much R code in this class that even though there's going to be some differences with this function, the main ideas are still the same. And if you really rely on those, you'll be just fine. But a few quick notes. So to accomplish these things, we're going to use the cv.glmnet function from the glmnet package. And what this does is it finds good, I'll put that in quotes, lambda values with cross-validation. Kind of like what the name says, right? So I put good in quotes because the authors of this package, Tib Shrani, I think he's an author, and maybe Hasey as well. I should know these things. They seem to be big proponents of not just using the lowest. Like let's say we're using mean squared error, root mean squared error, and we looked at it for each value of lambda. Actually a quick picture. So let's say this is lambda and this is mean squared, or let's call it root mean squared error, right? And let's say that you got results that looked like this. I didn't plan on drawing this plot, so this might be a little. I need to redo that. That's too difficult. It'll probably never look this nice, but just bear with me. Okay, so let's say you got this plot. It would be totally reasonable to select this value of lambda. But the authors of this package, and I tend to agree with them a little bit, say, well, we did cross-validation, so why don't we put error bars on those estimates and say, well, I want a value of lambda that gives me a root mean squared error that is within one standard deviation of the best and is a simpler model. So hopefully when we were talking about this, it was clear that the bigger the lambda, the less flexible the model. So that means that, let's see, if we extend this over this way, okay, well then we would choose this value of lambda. That's the 1 SE rule. So one of the nice things about this function is it always allows you to very easily obtain the lambda for both of these. They call it the minimum and then the 1 SE. And then you'll be able to use the predict function, the model, and then tell it which of those lambdas you want to use when you make predictions, but I'll let you see that when you get a tar. The more important thing that I absolutely need to tell you is that this cv.glmnet function has a parameter called alpha. If you supply alpha of 1, you're doing lasso. which I do believe is the default. And if you use alpha equals 0, you're then doing ridge regression. And one thing it does automatically, that's a really bad D, does scaling. So it takes care of scaling for you. So you don't need to worry about scaling it when you fit the model. You don't need to worry about scaling it when you predict on new data. It takes care of that for you. We'll deal with some of the minutia of that when we get there. But for now, just know that it's happening for you. And if you look at the documentation, you could turn it off, but I don't recommend that. Also, one thing that you'll find is that one not so great thing about this function is that it does not use formula syntax. So you're going to have to supply a Y response vector and an X matrix. And in the notes I have with a little bit of code, you'll see an example of that. But that is something you'll have to deal with. So you'll have to supply dummy variables for any categorical predictor, but don't make them manually. See one little code trick that I did in the notes. Sorry, I sort of lost my train of thought. Did we say everything we needed to? Yeah, we did. Okay, so one more thing. You can also do this with logistic regression. So we're not going to go into the details of that, but basically this whole idea, it doesn't just apply to linear models, it applies to generalized linear models, hence the GLM in GLMNet. So if you add a family equals binomial type thing here, you'll be rocking and rolling with a logistic regression with a penalty on it. Super cool. So yeah, and you'll play with that on the quiz. Yeah, so I think that's it. So that's our first of two sort of what I would call modern new ideas in statistical learning. So one last note that I leave you with. Everyone always asks me about this class, hey, why don't we do deep learning? To which I respond, because I want to focus on some basics and more practical things, and deep learning is just one really specific modeling technique, in my opinion. But this idea here, this idea of regularization or shrinkage, whatever you call it, is very related to a concept in deep learning called dropout. So if you ever find yourself reading about deep learning and you start hearing about dropout, think about how it relates back to this here. Okay, I've said too much. All right, so as always, if you made it to the end of the video, good job, and I'll see you in the next one.